Okay, right. So thank you everybody for coming. So I'm going to talk about what we call as L2N2, and it's a universal nearest neighbor estimator for intrinsic dimensionality and work which we've done on it. It's joint work with Omer, Primoz, and Gazina from Oxford. Yes, okay, so let me get started. So as an introduction, this work which I'm going to present today is going to be concerned about estimating the intrinsic dimensionality of data. So, in machine learning, we all deal with high-dimensional data sets, but they are not random things. So they have a certain amount of structure in them, and because of that, they tend to lie in low-dimensional manifolds. And then intrinsic dimensionality is a measure of the true degree of freedom of the underlying data, right? And it's lots of application areas, machine learning, computer vision, signal processing, material science, and things like this. So as an example, in terms of the visualization of image data sets, let's say isomap and MNIST digits, we find that even though the images are high dimensional, but they actually lie on quite a low dimensional manifold because, like for example, the MNIST image is of a 1, it doesn't occur in any possible configuration of pixels, which means that the actual number of degrees of freedom which it occupies is much less than the resolution of the image itself. Okay, so our goal is then to estimate this intrinsic dimensionality, let's say D, of the data set X, which falls inside a high-dimensional space of big D. Let's say in MNIST is 768, but for the images of the numbers inside this data set, it might just be 13 out of this 768 dimension. And how do we do that? We're going to propose an estimator which is based on the ratios of nearest neighbor distances. And it works well because it only uses simple mean statistics, and we don't need to know much or anything about the underlying distribution of the data, right? And therefore the distribution of the distances. Okay, so intrinsic dimensionality is not is quite a long study, or it has lots of research, which have already been done. And broadly speaking, we can split it into 3 groups of approaches. So we've got geometric and fractal methods, which are like correlation dimension, box counting, minimal spanning tree dimensions, and related things like this. That's the more classical approach. There are also other methods which are like projection-based. So one of the most popular ones is PCA, as we all know. You've got local PCA, you have MDS, you have isomap, and things like this. And then there is another group of methods which is related to our work, which is using nearest neighbors and distances to nearest neighbors. One of the early ones is Levina-Bickel MLE, maximum likelihood estimator. Then there is the 2 nearest neighbor approach, which takes the ratio of the distance between the second and the first nearest neighbor of points, and then tries to extract the intrinsic dimensionality. We'll see a bit more about that. There's a generalized version of that called GRIDE, and then there are others which incorporates other information as well, which is angles in addition to nearest neighbor distances. So these group of work, they tend to have certain amount of limitations. Theoretically, in order to prove what they prove, there is strong distributional assumptions. They need to know the underlying distribution of things which they are working with. There is also sensitivity to noise. When dimensions scale up, then you tend to need more and more points in order for it to give you a good estimate, right? So this is an example of what tends to happen. So if we were to take like points which are distributed uniformly on spheres of different dimensions, as given by the x-axis over there, and we extract a point cloud of, let's say, a few thousand points and fix it at that number of points, and then give it to all the different methods and say, now tell me what the underlying intrinsic dimensionality of the method is, And it will give something which tends to underpredict, as you see, 2 nearest neighbor, GRI, and MLE. Right? So our method, which is the L2N2, tends to be at this, and we shall see why in a short way. So okay, so before I can introduce our method, I'll talk about nearest neighbor distances and how it relates to dimensionality. Okay, so we are going to be using nearest neighbor distances to link it to the underlying dimensionality and see how it changes with it. So few notation. So if we denote X as a subset of a d-dimensional space, a point cloud, and really it's occupying just a small dimension, like a manifold, small d, right? And then for each of the points inside this big X, we can define the nearest neighbor, the cave nearest neighbor as such. So it's just the distance to the cave closest point, right? And one of the key ideas of all of this work and all of the existing nearest neighbor work is that ratios of nearest neighbor distances, different nearest neighbor distances, Rk over Rj, where Rk is the cave nearest neighbor, Rj, they reveal certain geometric information about the local dimensionality or the underlying dimensionality of the point cloud X, and that's what we will do. So what we can start off with, and to see how that is possible, consider a point cloud in d-dimensional, and we've something which we can control. So as an example, what I've shown here is a point cloud 2D, which has been obtained by a uniform distribution, and we take, like, let's say 500 samples, right, from inside the unit square over here. And another way of thinking about it is this point cloud can be thought of generated by homogeneous Poisson process, right, whereas the intensity is fixed, like some mu, and is homogeneous because so the distribution is constant across that. Yeah. Okay, so now if we have that point there, now what we can do is having big X as the point cloud generated by PBP. If we consider extracting for each of these black points here the distance of each of those points to the second and the first nearest neighbor, and then we just take the ratio, right? Like R2x over R1x for all of the x's inside this point cloud here. What we find, and it has been shown as well by the 2 nearest neighbor paper, is that the distribution of R2 over R1 is a Pareto distribution with the parameters 1 for one of its parameters, and d, which is the dimensionality of the data, like that. This is true. Well, they've shown this to be true for the case where the point cloud is generated by a homogeneous Poisson point process. Okay. Now, one thing to note from there is that if we see this distribution here, because R2 over R1 comes from this Pareto distribution, which has parameters 1 and d, then the one thing we find is that it doesn't depend on the intensity of the Poisson point process. Right? So if we increase the Poisson point process intensity, more points are generated in the point cloud. If we do the same exercise again, let's say for a smaller intensity, which generates, let's say, 500 points, we extract the underlying Pareto distribution, and it will be something. We increase the intensity, and let's say because of that, we are now generating 1,000 points. We again obtain another Pareto distribution when we calculate the first and second nearest neighbor ratios, and we do the same thing for 1,500, and it's all good. It's all nice Pareto distribution. But the interesting thing is, if we were to overlay all of those distributions together, we find that they're exactly the same, or they're very, very close to each other. Right? In other words, it's this distribution, the Pareto distribution, doesn't care about the intensity of the Poisson point process, which is generating the point cloud. Right? It only cares about the dimensionality. So if we were to change the dimensionality from, let's say, unit square to a unit cube to some 4-dimensional hypercube, it would still be Pareto distributed, but the parameters itself would be different. So the slope of this Pareto distribution would change depending on the parameters. Now, what's also interesting is that the proof in the L2N2 paper only applied to homogeneous point processes, which is this. Now if we just do the same thing for something which is non-homogeneous, right? Like let's say a Gaussian distributed set of points, or beta distributed set of points where beta is the distribution for the radiuses of the points from the origin, and extract various point clouds from that following this now non-homogeneous Poisson point processes, we again get Pareto distributions of the nearest neighbor ratios. However, in this case here, we find that even though the theory doesn't say anything about whether it works or not for a non-homogeneous case, when we put everything together, it seems to be invariant as well to the underlying distribution of the data, which is quite interesting, right? So here, the different histograms are shown by the different colored lines, but really you can only see one line here. So this is a nice empirical picture of what's happening here. So how do they use this, or how can we use this to extract the underlying intrinsic dimensionality? So you recall that the Pareto distribution has a PDF of this form, which is the dimensionality over x, which is the input point, to the power of d plus 1. So what you can do in terms of usage is that you have a point cloud as an input, you extract the second and the first nearer neighbor distances, that gives you a bunch of distances, you fit the Pareto distribution to this set of ratios, and that gives you some parameters, and you extract one of the parameter, the d parameter from the Pareto distribution, and that would be what your hypothesized intrinsic dimensionality of the thing. Now, in practice, there is other things which you have to do to get rid of outliers and things like this. But that tends to be the way of doing things. Now, one of the issues with doing this is, apart from outliers and related things, is that if you were to consider slightly different nearest neighbor ratios, not the second over the first, but let's say the fifth over the second, then you find that the underlying distribution of the ratios is now no longer Pareto, which means that you can't really do, you can't fit the Pareto distribution to that and then extract some kind of parameter and say that, now that parameter is the underlying dimensionality, because the distribution is completely different. Now, what you could do is that you could then try to figure out what that distribution of, let's say, R over R2 will be, and then redo the whole thing reuse the proof and try to fix the proof, which L2N2 has done. Now, which tends to be, is every time you need to figure out what the distribution is, and then you have to change the proof again in order to be confident whether it works or not. So that's one of the issues at the moment. You need to know what the underlying distribution of the ratios are. And then there are other things where, theoretically, we don't know, or there's not very much knowledge about what happens when we are dealing with non-homogeneous Poisson point processes. So the proof only applies to homogeneous Poisson point processes, and it would be good to be able to extend that to non-homogeneous ones, because empirically we can see that it does work even in a non-homogeneous case. So that's our contribution to these shortcomings here, and this is the L2N2 intrinsic dimensionality estimator which we have proposed. And this is it's based on nearest neighbor ratios as well, but we have chosen to extract an estimator which is the log of the ratios over here. Now, the reason why we chose log is because it tends to stabilize things like the ratios, right? So when you're just talking about RK over RJ, then there can be things which have big influences, right? Small RJ versus big RK, then you could have like outliers all the time. If you take a log of that, then that sort of dampens those changes. You take a log, then it further dampens things, so it sort of spreads the mass, in a more uniform way, and that helps quite a lot in many ways in terms of empirical when we are doing it, using it in practice as well. That allows us to transform this ratio into a statistic, with a predictable asymptotic form. So, what are we working with? We are working with something quite simple. So we take the log of these negative log of the ratios, and we just compute the mean. So it's the average statistic which we are working with. Now, what's the advantage of this, right, versus what we've seen so far by the two nearest neighbor method? We don't need to fit any underlying Pareto distribution to our set of extracted nearest neighbor ratios. All we do is we compute the ratio and we compute the mean and all that. Right? That's in practice what we are going to do. Theoretically, we show that this average of nearest log nearest neighbor ratio, is log d plus some. So d is the dimensionality plus some constant ckj, which depends on your choice of nearest neighbors. Right? So it's a linear dependence between lkj and log d. The constant doesn't depend on the dimensionality, and I guess most importantly for us is that it holds independently of the data distribution, right? And we're still considering some point processes, but now this result extends to both homogeneous and non-homogeneous, unlike previous work, for some point processes. So before I go on to say why theoretically, maybe I'll talk about how we actually use that. Right. So we have a linear relationship in the past, and really, it should be 1 times log d plus ckj. But in practice, we tend to just put some kind that, because we are dealing with finite sample sets, then we have a scaling constant of alpha and an offset constant of beta to take the place of this ckj and to account for finite biases, right? So if we have this relationship here, right, which is this is our average of logs of ratios, and this is some constant which we will estimate, let's say from our data. We only have to do it once for some data set, and it should apply for a lot of other things because it's independent of the distribution of the data, right? So we have log d over here, and we're really interested in actually extracting d. So if we solve for d, then we get this exponential relationship here. Now this should be over alpha, but never mind. So, but it's just an exponential of the scale and offset version of the mean of the minus log of the ratios over there, right? And because it's, I repeat again, because it's this estimator here does not depend on the data set or its distribution, then we can get away with just estimating alpha k and beta kj once for a fixed k and j, let's say second over first nearest neighbor. Okay, so there is some amount of parameter tuning. This comes back to what I was saying just now. So in theory, alpha kj should be 1, and beta kj should be ckj, which is a constant which we can calculate. But in practice, because we are not using an infinite number of points or a huge number of points, then finite numbers of samples will induce some kind of bias to the estimator. So what we've chosen to do in practice is to empirically learn this alpha and beta constants. And one way of doing that is we have a syntactic Gaussian data of known dimensionality d, which we can generate. And we generate point clouds of this. We extract their average statistics of this nearest neighbor logs. And then we just fit using least square regression, the slope and the offset, which will give us alpha and beta over there. Like for this, as shown in this graph over here. So if we generate point clouds using Gaussians of different dimensionalities, we will obtain points around here on which follows a certain line for a fixed neighbor, nearest neighbor choice, let's say of the fifth and the third, and we will get this. And what we do is we fit the line over here, and that will give us the alpha and the beta, which we require. And if we have that, then we can plug that into this equation here, and we will be able to then use our estimator. Now, there are many choices, for which nearest neighbor configurations we should use. The first over the second over the first, the fourth over the second, and so on and so forth. Experimentally, we found that the second over the first performs the best overall. But you'd think that a larger K would be a better thing because it's more global, right? But because we have finite samples, then when we are using bigger K, then for small data sets, you might skip to a completely non-local region. So in practice, unless you have a lot of points, second over first nearest neighbor tends to be the better way of doing that. Right, okay, so that's how we will use it. We will see some experimental results on that shortly, but before that, it'll be good to be able to give some kind of theoretical justification for the statement, which is that this is independent asymptotically of the underlying data distribution. So how do we do that? The goal would be to show that this statistic, which is this bar LKJ, given some point cloud of n number of points, converges to some function of intrinsic dimensionality d, in this case log d plus some constant over here. And we also at the same time want to say that this happens independent of the underlying distribution of the data. So this is the main theorem. One assumption is that our data is sampled from a density F with small number of requirements, but that covers everything which we usually deal with. But it's from a C1 manifold, right? So what does the theorem say is that this average of the log of nearest neighbor k over j converges in probability to this log d plus ckj, where d is dimension at ckj only depends on the choice of nearest neighbors which we want, and is independent of the manifold and the density provided. The manifold respects the assumption there. And because of that, we rearrange this for D, we get a consistent estimator for the underlying intrinsic dimensionality of the manifold, which is this. Right? So it's exponential of our statistics minus this beta over alpha. That should be the right way. So how do we show this? There are three main components to proving this, and I'll give maybe an intuitive picture as opposed to the technical details of what it is. So the first one is that is what it calls a local Poisson approximation, right? So the idea is that you will be able to get away, if you have a non-homogeneous Poisson point process, you'll be able to get away with just looking at a local neighborhood around a point in our point cloud, and as the number of points increases, that sort of, on a local neighborhood, looks like a homogeneous Poisson point process with different intensities on different points, but for one point, it's sort of like a homogeneous, nicely uniformly distributed process. And looking at a nearest, sort of local neighborhood involves, let's say, truncating, right? I'm not going to care about nearest neighbor ratios, which are too big, right? I just only consider things which are reasonable in size, but we then have to show that it doesn't matter. It's like once your intensity goes high enough, everything is close together anyway. So even if you are limiting yourself to looking at a small number, well, a limited finite range of nearest neighbor distances, that's fine. And then if you have this too, what we are showing is that you can deal with things locally separately, and locally dealing with things doesn't matter because it's the same as not when it's homogeneous. And after that, then we can extract a relationship between this statistics LKJ and the underlying dimensionality D over there. So the first one, which is this, we work with this, what is called LKJR. So that's just what we've seen just now, which is the log of the average of the log of the kth over jth nearest neighbor distance, but now restricted to it having values less than r, right? The nearest neighbor having within a certain fixed radius r over here. And what we can show is that if you, for any fixed r, as you are ramping up the number of points or the intensity, that this LKJR will converge in probability to the average, local averages. So this is like well, mixture of homogeneous Poisson point process, right? Because this one here, this is a Poisson point process with intensity fx. Fx is just you know, the likelihood of at x in on the manifold there, right? But we can treat it as though it's just a locally uniform distribution. But and because we are dealing with nearest neighbor, we we might as well be considering a Poisson point process on the origin with intensity fx, right? So that's what this is saying, that this, we can just decompose it into each of the individual points in xn, treat it as though it's just a local Poisson point process up to radius r, like this here. And in the proof that for this lemma here, we would show that this is the same thing, right, in probability. Okay, right. So that allows us to deal with this. Essentially allows us to say that this restricted LKJ up to radius r, is almost like dealing with a non-homogeneous case, right? Because we have the different fx for the non-homogeneous Poisson process. So that's one. Now, again, it's like we might worry that in restricting what nearest neighbors, which distances which we are considering, that maybe that would cause us a problem, right? So there's another lemma which tells us that don't worry about it. So as our intensity ramps up, the difference between this LKJ and LKJR is getting smaller and smaller, such that the probability of them being different tends to zero, right? So intuitively, this lemma tells us that we are able to ignore very, very far away neighbors, outliers, or if you are in points which are in sparse regions, because as we ramp up the intensity, there are going to be many more and more points in the local region of radius r in a point, right? So all of its kth nearest neighbor at some point, when the intensity is high enough, will fall inside this radius r over there. Right? So so this, as you add more data, the probability of having a far away neighbor essentially goes to zero. Far away meaning greater than r, let's say. Okay, then the last thing which we need is, of course, we have this LKJ. We're going to take the average of that. Now, if we push that all the way to infinite number of the asymptote, we will have an expectation of this LKJ, right? And now let's say if we are just going to consider a homogeneous version of this at the origin, doesn't matter where it is because it's translation invariant, then there is this lemma which says that the expectation of this homogeneous rate lambda Poisson point process of this log of nearest neighbor ratio is essentially log d plus some constant ckj. And this is simple enough that I can sort of show how, or talk about a little how we do this, right? So how we prove this. So if we consider, it's our nearest neighbor distance rk to some point, what we have is, instead of considering the distance itself, we consider the volume of a ball of radius rk, right? Like yk in this case here. In Poisson processes, we have a bunch of points which have been generated by the point process, y1, y2, y3, bunch of balls, and effectively their arrival times. Then we can show that ratios of them, like j over k, will follow a beta distribution, right? But importantly, because we are dealing with volumes of balls, then they tend to be related, proportional to the radius to the power of d, right? Now, if we are working with yj over k, where we know that it's a beta distribution, that's a nice thing which is because it's Poisson process and it's this kind of arrival time. We know that it's a beta distribution. We can convert yk over yj back into distances by just taking the diff root of this ratio over here of volumes. And then finally, if we take the log of those, which is what we are doing in the first place, that will pull the d down, right, outside, which will then give us this form up here over here, which will be log d plus some constant, which is the integral of the underlying this beta distribution. Right, okay, so that's all. That's the three pieces of things which we need. So now we can chain them together and we will get our proof for why this thing here up there, which is LKJ, converges in probability to log d plus this constant over here. Now the first thing is, we can deal with this non-homogeneity using the first step, which is we express our restricted LKJ to R as essentially an average over local Poisson models with different intensities. Right? Now, we then show that don't worry about restricting it to R, because at the limit, RKJR and LKJR and LKJ is the same thing. Right? So they converge to the same value. Now that it's the same thing, then we can apply the third step, which is if they are the same thing, and we know that it's essentially it doesn't care about the intensity because it's homogeneous. Then we can extract the dimensionality d over there by taking the log, and that gives us our result. Okay, right. So now we can go into experiments. So that's the theory. So how have we shown that experimentally it does a good job and potentially better than existing approaches as well? So before we can run experiments on that, we need to do some kind of parameter tuning. So to estimate these coefficients alpha betas, and what we do is we generate 1,000 point Gaussian point cloud across a number of dimensionality. And what we then do is we get a bunch of xy's, which is LKJ versus the dimensionality, and we can fit a straight line to that, and that will give us the required coefficients alpha and beta for our dimensionality estimation. We just do it for the Gaussian point cloud, and we will use it for everything else, right? Whatever the underlying distribution is for the same number of points. So what have we tested it on is there is a benchmark manifold data set, consists of 24 synthetic data sets of known ID because it's synthetically generated. We compare against 14 other existing methods. So this data set was chosen because it's popular against intrinsic dimensionality estimators. Is used to evaluate how good they are. And the choice of evaluation metric is just what they call as a mean percentage error. And the definition of that is just the percentage of the absolute, well, it's just the how much the true dimension versus the estimated dimension differs, right? So 100 minus the difference, and it's absolute, so it's any deviation more or less would bring in an error. Okay, so so as an example, well, this tells us what kind of manifolds we are dealing with. So it's 24, maybe less than 24, I think we should show here, but a bunch of them. And what they have is they have different ambient dimensionalities where we have embedded smaller dimensional manifolds in there. So we've got our normal things like spheres and cubes, hypercubes. We've got various kinds of exotic non-linear manifold, which are really strange. Now, one thing which is noteworthy for these kinds of manifold is that whether by nature, whether it was intentional or not, the underlying distribution of the points in these manifolds tend to be sometimes non-uniform. Now, they generate things in a uniform way, but once you transform them into this more non-manifold structure, it tends to be clumped in certain ways, which is non-uniform. So that's an additional challenge there. So many different types of manifolds with different structures, different dimensionality. So it's a good data set to use to benchmark our points. Right. So I've shown this before. This is just our parameter tuning for estimating the alphas and betas. Alphas would be the slope of these lines, and betas would be the the offset which is required now is different for different nearest neighbor choices. But again, you just have to do it once and then you just use those values there. Now, if we do that and then we then test it on estimating the intrinsic dimensionality of our manifold data set, and we compute the average mean percentage error over, say, 20 repetitions, we come up at the top. L2N2 is pretty much always better than all of the other existing results, which is, there's a huge bunch of them. Our two closest competitors is 2NN and Gride. They get about 13% error in general. We get about 11 to 8% depending on, there's a rounded version and there's just another non-rounded version. So this is the number of points. As we increase the number of points, everybody gets better, but we get better faster than everybody else. So that's good. That's a good thing. So we perform well. Of course, we don't perform well all the time everywhere. There are certain things where we don't do so well on. And this is an interesting. I put this slide here because it highlights something interesting as well. So if we look at the green bar here, again, this is the x-axis is the average mean percentage error. Higher is worse. And the different colors are the different methods here, except for these three, which are blue, orange, and green are our method. But if we look at green, this 8-4 means that we've chosen the 8th nearest neighbor over the 4th nearest neighbor distance for the ratio. And we find that for low dimensional things like helixes, right? So these are embedded one-dimensional helixes embedded in a three-dimensional space. When the neighborhood choice is too large, then it's a detriment to our method. And one of the reasons is because, if you imagine a helix, one point the 8th nearest neighbor might be on another part of the helix which is non-local, and that would skew all of the statistics, and that would cause the dimensionality to be potentially overestimated. And we see that in this ones here as well. But for the second over the first, then it tends to be better, especially for certain non-linear things. Okay, right. So that's synthetic stuff. We can also run our things on real-world data sets like images. So what we've chosen is isomap, CIFAR, isolate. So these are like images of faces, like isomap and isolate. And CIFAR is just 100 different objects of cars and aeroplanes and things like this. Now the challenge with these kinds of experiments is that we can extract some number. Other methods will extract some numbers from the input images. Nobody knows what the actual number ought to be, right? So it's who knows. But if we're not too far away, then that tends to be a good thing. So in general, we predict a higher dimensionality than existing methods. But I would like to say that maybe we are more correct because we tend less to underestimate compared to other methods. So other methods tends to underestimate prediction, in particular when there isn't enough number of points, and we do so less than them. So maybe us predicting a bigger dimensionality is not necessarily a bad thing as well. So if we look at MNIST, the same thing happens as well for different digits, like 1, 2, 3, and 4 as an illustration. So always we predict higher dimensionality, intrinsic dimensionality for the digit images. Now one way of checking that is using this downstream experiments. So how do we do that? So we can indirectly probe the potential actual intrinsic dimensionality using autoencoders. How do we do this? We create an autoencoder architecture which takes in as an input 768 dimensions and then bottlenecks it into something, let's say 256 hidden units, and then some hypothesized intrinsic dimensionality number of hidden units, and then expands it all the way back to its original dimensionality, and then does a reconstruction, which is what the autoencoder does. Use ReLU and use reconstruction error as the training loss. So if we do this across the number of different hidden units for this bottleneck layer here, what we find is that if we have too few of the bottleneck layer, then of course the final reconstruction error after training will be high. Now, if we start increasing the number of hidden units, then at some point we will get enough of them, right? And then our reconstruction error will be good. And increasing that number of hidden units after that will not really benefit the reconstruction error too much after. So we can tally this, leveling of this MSE versus our estimated intrinsic dimensionality versus that of, let's say, 2NN. Right? So the green points here are what L2N2 says is the intrinsic dimensionality of the different digits of MNIST. And we are always we predict greater intrinsic dimensionality compared to 2NN. And so if we look at where 2NN is, it tends to be of where it predicts, and we set that to, let's say, 2NN's prediction to the number of hidden units in the bottleneck layer. It tends to have a higher MSE, which can be improved by increasing more. So which sort of indicates that maybe that's not really the actual number of dimensionality of the data. It's too few, right? And so the bottleneck layer is too tight, and you can solve the problem better. Now for us, after that, the MSE in most cases anyway tends to start to in fact almost level off, which sort of indicates that maybe we are predicting the intrinsic the dimensionality which is closer to the true intrinsic dimensionality. Okay, so the last thing which we can do is to analyze this thing called grokking in deep neural networks. So grokking refers to delayed generalization. So you can train a model for a long time, nothing happens, until suddenly the test error decreases suddenly. So there are different phases to DNN training. At first, the model, the initial phase would be it starts memorizing the training data, after which it goes through a terminal phase where it starts generalizing. So the observations is that training goes to 100% accuracy very quickly. But test accuracy tends to remain not good for a long time, but then there's an abrupt generalization. Now, in all of these cases, we need weight decay to make the weight smaller and smaller. Now, nonetheless, there is this phenomenon says that there is a transition from memorization of data to structured representation extraction from the DNN somehow. So we'd like to understand a little bit more from maybe the point of what's happening in the intrinsic dimensionality of the data. So the setup is this. We have a fully connected neural network with 200 hidden units, just 3 layers, which I didn't say. And then there is, we're training it with just stochastic gradient descent with weight decay for a very large number of people, 180,000 in total. In this case, we only use 10% of the training data, but we tested on all of the test data here. So what happens? We see that this is a log scale. We see that the training accuracy goes up really fast. Within 1,000 epochs, it's done its job in terms of the training accuracy. It's 100%. But the test accuracy, it's not very good at all. And we have a challenging data set, which is adversarial, like corrupted test data, which is intentionally corrupted to make it even more difficult to classify. And it sort of keeps training, but then there's a sudden increase in the accuracy of the test data, and the same thing later on for the more challenging adversarial data as well. So what's happening there? One way of looking at it is maybe if we look at it from the lens of intrinsic dimensionality. There is it represents the effective number of degrees of freedom in the representations, often much less than the actual, let's say 200 dimensions. So we expect, hopefully, that in grokking there is a sharp drop in intrinsic dimensionality, where things are now aligning with each other, so that the DNN is no longer it's not overlearning things, right? So this is the result which we get finally. So these are the intrinsic dimensionalities of the outputs of different layers of a DNN as we are training it from the start to 180,000 epochs. And we can feed it, and then we extract what's the intrinsic dimensionality from there. And we see that not very much happens in the initial learning stage, where the training error is now 0%, but the test error is still very high, up to a certain point where suddenly there is a sharp drop, right, in the underlying intrinsic dimensionality, and there is some kind of, and there is some, so it's still not understood for us anyway what is the cause of this, but at least we are sort of observing this now, this change in the DNN. All right, okay, so almost done. So in summary, I think what I presented is our work on estimating intrinsic dimensionality on high dimensional data using statistics of nearest neighbor distance ratios, right? When we take a log-log transformation of that nearest neighbor distances, we get this universal linear relationship between our average of log-logs of ratios. It's sort of linearly related to the log of the dimensionality plus some constant. And it's distribution free, geometry free, with the manifold assumption. Yeah, and I think we've shown that it's sort of state-of-the-art empirical accuracy as well. Of course, it's not all done. There's still quite a lot of things which we need to work on as well. So there is a finite sample sensitivity, right? So it's asymptotically, we know that L2N2 converges to this log D plus thing, but in terms of finite number of samples, we are not necessarily very clear about how fast things will converge. The choice of K over J is also another thing which is an interesting question. You expect that with enough points, larger values of K and J maybe might do a better job, but how many more points do you need? So the theoretical information about that is still an open question for us. We assume C1 manifold with bounded density. So what happens if we try on more different types of structures, fractals, discontinuous data sets, or data sets which are a mixture of different dimensionality manifolds or structures? So don't really know what will happen there. So future work is basically to solve or try to tackle these questions here. Small sample accuracy, if we know more about the convergence rate, that would help. It might be worthwhile understanding, the distribution of LKJ, not just the mean, and then extend it to maybe results to other structures, fractal or stratified structures and things like this. Study different KJs and look into noise robustness even more as well. Okay, and that concludes my talk.